Right, lesson 3.3, common factors of a polynomial. In this lesson, what we're going to be using is some of these skills we've learned with the LCM and the GCF, and moving that forward to use it with polynomials. Polynomials, I hope you remember, they're basically algebraic expressions that have variables and constants. So for instance, what could I write up here? 2x squared plus 4x plus 8, that would be an example of a polynomial. All right. And so, like I said, we're going to be trying to factor those. As we factor, we're going to be using algebra tiles, and I find that a lot of students are kind of negative towards algebra tiles these days because they've been used all the way through from grade 8 to grade 9 and now in grade 10. But they're important for the one reason that I think it explains to you the why. Why does something factor? Rather than me just giving you an algorithm that's going to work all the time, you should be able to find out kind of why something works. Right? So the first thing I have here, it says using a set of algebra tiles, sketch below all the different ways you can form a rectangle with the given tiles. Beside each of your sketches, write a multiplication sentence to represent your rectangles. So using the algebra tiles here, I have 8 x's would be right there, and I have a 4. All right. So for instance, I'll show you how I could do this. I'll give one for you, and I'd like you guys to try and find the remaining ones. So if I take the 8 x's and I take the 4 and I arrange them into a rectangle, what you're going to see is that's going to allow me to factor this. So for instance, imagine I had 1x, 2x, 3x, 4x, 5x, 6x, 7, and 8x. And then I put the units right here. 1, 2, 3, 4. So these are the ones. I know I did them all in red for right now, but this will just give you an idea how it could look. Like so. Well, if you look at the top here going across, I have x times, I have x, x, and a 1. That is 2 x's, and I could write plus 1. And on this side I have 1, 2, 3, 4, so I can write 4. Well, the interesting thing of this is if you go 4 and you multiply it by 2x plus 1, you get 8x plus 4 when we use our distributive property. Sometimes you've heard me call it feeding the chickens. All right? And so that shows us one way that you can go and factor 8x and a 4. If you pop out a 4, essentially, you've factored out a 4, you still get the same thing, just modeling it with algebra tiles. Okay? So I'd like you to try to develop as many of those as you can. It's actually fun. Like I don't even expect you to write them down. Just go get some algebra tiles, do the activity. Obviously, this is one you'll have to do in class. Otherwise, you will have to write them all out. Okay? So let's mosey on down here. When we write a polynomial as a product of factors, we factor the polynomial. The polynomial is fully factored when it cannot be factored further. As an example, if we come up here, the 2x plus 1. There's nothing else that I can factor out. I can't take out a variable. I can't take out any constant. So I'm good to go. All right. What I'm going to do here now is I'm going to compare multiplying and factoring in arithmetic and algebra. So for instance, when we multiply factors, we form a product. So if I take 4 times 7, I get 28. And then if I factor a number by writing it as its product of factors, I can write 28 as 4 times 7. All right. Well, the same thing works when we're dealing with algebra. If I ask you guys to expand this using the distributive property, we're going to have 3 times 2 is 6, and then 3 times the negative 5a is negative 15a. All right. Now, conversely, I can go backwards. I can look at 6 minus 15a. I can say, what's a number that I can divide out, essentially, out of all those terms? Well, since the first term doesn't have an a, I can't take an a out of everything. But I do notice that 6 and the negative 15 are all divisible by 3. So when I divide by 3, what I'm left with is 3 times what gives me 6, so it would be a 2. And 3 times what gives me the negative 15a? Well, that's going to be the negative 5a. And the big thing I just want you to understand right here is that in both of these, all I'm doing is these are basically considered inverse operations. All right. So for instance, when we add something, we can take the inverse operation by subtracting something. You get back to where you're at. Right here, you're seeing that expanding, which we've done a little bit more of in the past and compared to factoring, is really the same thing, just backwards, right? So expanding and factoring are inverse operations. All right. So let's take a look at a couple examples. I'm going to show you how you can be using the algebra tiles to solve these, and we'll also be looking at a method using the greatest common factor. All So let's see what we got here. So the first one I have is 3g plus 6. You may already be able to figure out how to factor these, although believe it or not, on the provincial exam, they'll be giving you ones where you have to factor using algebra tiles. Now, obviously, they won't be making you actually manipulate them, but they'll be giving you solutions that algebra tiles have been used with. So resist the urge to fast forward here because you do need to know this stuff. So to deal with this in algebra tiles, what you're going to do is you're going to arrange the tiles to form a rectangle. Alright, so if you take 3g plus 6, I'm going to take, let's say, 3g. So remember, your g's are just like your longer tiles. So I got 3 of them there. And now I'm going to try to arrange them into a way to form a rectangle. Now, if I just started putting, let's say, this 6 right here, you'd see I'd get maybe something that looks like this. It clearly does not form a rectangle. So as a result, you're going to have to look in some other way. What I notice right here now is if I go and take this, I put 1, 2, 3 there, and another 3 there, I get a lovely rectangle. Alright, so these are my g's, and these are my integers right here. Well, now if you simply just look at the side lengths, let's say I'll take this top one up here, I have a g and a 2, so that is g plus 2. And if I take this side, a 3, you've therefore factored this. Alright, so we can say that we can write 3g plus 6 as the factors 3, all multiplied by g plus 2. Alright, it's one way using algebra tiles. You might want to try this next one on your own here using d squares. Now the d squared ones are a little bit tougher. You're just dealing with the squares though, right? So I know I gave you 12, might be a little bit of an overkill here, but we got 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. Alright, now you notice why I put them in this order is because I'm trying to think, is there a number that goes into 8 and 12, and I'm noticing that it could be 4, so this may help me right here. So imagine if I have 8 of these d's, I could put 2 d's here, 2 d's here, 2 d's, but then I have 2 more d's to distribute. I can't distribute them evenly to make a rectangle. But if I do it on this side, you can see I can just put, oops, make these a little skinnier. 2 d's there. 2 d's there, 2 d's there, like so. Alright, so these are all d squareds, and these were all d's right here. And then we have this factored. Alright, so along the bottom side here, we can see we have 4 d's. Along this other side, I know you may think that this is a d squared length right there, but it's just a length of d, a length of d, a length of d. So we can write this as 3d plus 2. And the interesting thing then is, of course, if you go and write the original question, we write it as its factors right here, 4d times 3d plus 2. You'll notice that if I was to go in, expand this, distribute it in, 4d times 3d would give me the 12d squared, and the 4d times 2 gives me the 8d. Alright, so that's one method of doing it with algebra tiles. I'll show you guys a different method of doing the same question. So recall the first question was 3g plus 6. What we can do is, using the greatest common factor method, just go and take the 3g, take in each individual term, so I'll take the 3g right here, and divide it into its, or basically factor into its prime factors. So 3g, I notice that it has a factor of a 3 and a g. That one's not too exciting. But 6, I can go and take it and say, okay, I know that 2 goes into it, it's a prime number, 2 times 3. Alright. Now if I highlight this, you'll notice that 3 is a factor of both of them. So therefore, if 3 is a factor of both of them, that leads me to believe that I can factor out that 3. So 3 would be my GCF. Therefore, I can say 3g plus 6 is equal to 3. If I factor out a 3, then what would I have left? I would just have a g plus 2 left. And now, as you progress, you guys are just going to be able to do this in your head. You're going to be able to look at this and say, okay, I notice I can take a 3 out of all those terms. There you go. You're not really necessarily thinking, what is the GCF? Because it's just going to happen naturally. Now let's look at that next one that was a little bit tougher, the 8d plus the 12d squared. If you start with the 8d, alright, we know that we have a 2 that divides into it. So if I divided it by 2, I'd have a 4d. If I divided it by 2 again, I'd have a 2d. And if I divided it by 2 again, I would just have the d left. So I can write this as 2 times 2 times 2 times d. Okay, let's deal with the 12 d squared. Again, I can divide it by 2, divide it by 2 again, and then by 3. So 2 times 2 is 4, times 3 is 12. And then since I have a d squared, I can write it as d and a d. And then simply, folks, I'm just looking for what is common. Well, I have a 2 and a 2, 2 and a 2, and a d and a d. So therefore, it means that my GCF is 4d, 2 times 2 times d. So we can write this now as 8d plus 12d squared is equal to 4d onto 2 plus 3d. Okay, it makes no difference what order you put that in. I think I did it different for the one above. Okay, let's turn on to the next page and try some that are a little bit more difficult. So the next one says, when a polynomial has a negative terms, or 3 different terms, we cannot remove a common factor by arranging the tiles to form a rectangle. Instead, what we do here is I want you to arrange the tiles into equal groups. So this first one that we have here, 5 minus 10a minus 5a squared, all we're going to do is just try and group it. All right. So if we look, we're going to try to distribute this into, let's see, a number that goes into 5, negative 10, and then negative 5. Well, therefore, I'm going to distribute it into 5 groups, seeing as 5 is a multiple of all those. Seeing as there's not an a in all the terms, you don't have to worry about dealing with the a, so we're just going to, like I said, distribute into 5 groups. All right, I'm going to go ahead and distribute this polynomial into 5 groups. But in order to do that, because I have positive and negative terms here, I'm going to use a little bit of a key here. So for positives, I'm going to use blue. And for negatives, I'm going to use red. So just keep that in mind right up there. So let's start out with the 5 units that we have right here. I have 1, 2, 3, 4, and 5. So this is where I'm going to put my 5 groups. Now I have my A's, so my A's are the longer bars. Now, since I'm dividing them into 5 groups, and each one of these groups has to get 2 large bars like that. Okay, so that's my negative 10a, and then lastly I need to distribute out the negative 5a squared. So that means I'm going to have one of the big negative 5a squareds in each one of them. All right, like so. And so what we can see now is if you take a look, in each group we have a negative 1, we have a negative 2a, and we have a negative a squared. So we can say that this has been factored to be 5 brackets, because we have 5 different groups, onto whatever's in each group, 1 minus 2a minus a squared. So if I was to go back, like I said, remember expanding is just the opposite way of factoring, and expand all this out, you would see that I would get back to my original question. All right. Now we can also do this, of course, using the GCF. All right. So I'll just write down the question right here. Again, it was 5 minus 10a minus 5a squared. We simply just look at each one of these terms, and we're going to see what the greatest common factor is. Well, 5 is a prime number, so it's its own. All right, now we'll look at 10a. 10a, if you prime factorize it, you'd have 5 times 2 times a, and 5a squared, you have this one as 5 times a times a. And once again, the only thing that shows up in all of them is the 5 and the 5. So therefore, we can say that to factor this one, you have the 5 would pop outside, and then you just write what you have left. So think about dividing this term by 5, you'd have a 1. Dividing this next term by 5, you'd have a negative 2a. And dividing the last term by 5, you have just a squared. Right. So that's one method of doing this. I think you guys are going to lean towards doing the greatest common factor, but you'll see in my assignment I made you do some that you have to use algebra tiles for that. All right. So once you're finished here, I want to make sure that you guys know how to check your solution. And that's kind of what I was just talking about right there. And so we check our solution by expanding. And so if I was to take what I have right here and expand it, you'll see I would have 5 times 1 is 5 minus 10a minus 5a squared. If you ever expand something and you do not get to the original question, then it means something has gone wrong. So in this time it worked out, so I know that I got it right. Our last page here. This one I'm going to show you how I would normally factor this. And so this is once you've built up your skills, you're going to see it's a little bit easier. All right, so it says, factor each trinomial, verify that the factors are correct. I put a